Hi everyone. If you find this helpful, please like and subscribe. Let's jump right into today's topic.
Have you ever wondered how we can pinpoint the exact elements, the building blocks, inside almost anything, like the steel in a skyscraper, or maybe the tiny components in a microchip, and often, in just seconds?
It's a really fundamental question, yeah.
Yeah.
And it touches so many areas.
Well, today we're taking a deep dive into a technology that does exactly that, with pretty surprising precision and speed. It's called optical emission spectrometry, or OES for short.
Right. And our mission today really is to unpack the fascinating science behind OES. We want to explore the different ways it's done, the different forms it takes, and discover where this incredible technology is making a real difference out there.
Yeah, everything from, say, making sure your car is safe to maybe even groundbreaking medical research. We'll compare it to other methods, too, and peek into its future.
And we're aiming to break down some, potentially complex stuff into clear, digestible insights.
Exactly. Hopefully giving you those aha moments so you feel really well informed without getting, bogged down in heavy jargon. So let's peel back the layers. What actually is OES?
Okay, so at its core, OES is a sophisticated way to do quantitative analysis. It figures out the elemental composition by measuring the light that gets emitted from excited atoms inside a sample.
Excited atoms.
Yeah, and here's where it gets really interesting.
Yeah.
Each element, each distinct element, has its own unique spectral fingerprint. It gives off light only at specific, very characteristic wavelengths.
It's like a signature tune, but with light.
Precisely. It's all rooted in quantum mechanics. You have electrons orbiting the atom's nucleus at specific energy levels, right? Discrete levels.
Okay.
When energy hits them, say from an electrical spark, these electrons jump up to a higher energy level. They get excited, but that state isn't stable.
So they want to fall back down.
Exactly. And when they fall back to their normal lower energy state, they release that extra energy as a photon, a particle of light. And the crucial part is that photon has a very specific energy, which means a very specific wavelength or color corresponding exactly to that energy jump down, unique to that element.
Got it. And you mentioned it's quantitative, so we can tell how much is there, not just what is there.
That's right. The intensity of that emitted light, basically how bright it is at that specific wavelength, is directly proportional to the concentration of the element in the sample.
Ah, so brighter light means more of that element.
In simple terms, yes. There's a physical principle behind this called the Boltzmann distribution, which basically governs how atoms populate different energy states at a given temperature. It ensures that relationship between light intensity and concentration holds true.
So that scientific rule, the Boltzmann distribution, that's what lets us reliably turn how bright into how much.
Exactly. It's the physics that underpins the quantitative power. So OES tells you what elements are present, that's the qualitative part, and how much of each the quantitative part.
And you mentioned the light spectrum it uses, 130 to 800 nanometers. That sounds pretty broad, covering UV and visible light.
It is broad, and that makes OES incredibly versatile. It means we can detect a wide range of elements, including the lighter ones like carbon, sulfur, phosphorus, boron, nitrogen.
Which can be tricky for other techniques, right?
It certainly can be, so that wide window is a real advantage.
Okay, so that's the what. Let's get into the how. How does this whole process actually work? From sticking a sample in to getting a reading out.
Right, so it kicks off with applying intense electrical energy to the sample. Often this is done using an electric arc, or a spark. And this happens inside an atmosphere of inert argon gas.
Argon, why argon specifically? Why not just air?
Ah, good question. Argon is crucial. It's inert, meaning it doesn't react chemically. Using argon provides a stable, predictable plasma environment. If you used air, the oxygen and nitrogen would react with the sample at high temperatures, creating oxides and nitrides, and that would totally interfere with the analysis.
So it keeps things clean and controlled.
Precisely. It ensures the results are consistent and accurate.
Okay, so you hit the sample with energy in argon. Then what?
That energy vaporizes a tiny bit of the sample surface. It turns it into this superheated gas called a discharge plasma. Think of it like a tiny controlled lightning strike.
And inside that plasma?
Inside that plasma, the atoms and ions from your sample get energized or excited, like we talked about. There are complex things going on, electrons from the plasma hitting sample atoms, bumping their electrons to higher energy states.
The excitation stuff.
Exactly. And then almost immediately, those electrons fall back down, releasing photons emitting light. That's the radiative decay. There are other processes too, like collisions de-exciting atoms, but the key thing is generating that light, that composite glow, containing all the different spectral fingerprints.
So you have this mix of light coming off the plasma, all the different wavelengths jumbled together. How do you sort them out?
That light is channeled into the spectrometer itself. And inside, there's a key component, usually a high-precision diffraction grating. Think of it as a very sophisticated prism, but much more precise.
Okay.
This grating spreads the light out, separating it very precisely based on wavelength. So it takes that jumbled light and organizes it into a spectrum, like a rainbow, but with sharp lines at specific points corresponding to each element's emission.
And then you just need to measure those lines.
Essentially, yes. Specialized detectors are positioned to capture that separated light. Historically, these might have been photomultiplier tubes or PMTs, but today it's mostly solid-state detectors like CCDs or CIDs, charge-coupled devices or charge injection devices.
It's like in a digital camera.
Similar technology, yes, but optimized for spectroscopy. They measured the presence and, crucially, the intensity of each specific spectral line.
And that intensity tells you the concentration.
Right. But it's not quite that simple. That measured intensity has to be correlated back to concentration using calibration curves. These curves are established beforehand using certified reference materials, or CRMs.
So you need known standards to compare against.
Absolutely. High purity, well-characterized materials with known elemental concentrations. Building and maintaining good calibration is fundamental to getting accurate quantitative results.
You mentioned challenges earlier, like matrix effects. Does the calibration help with that?
It does, to an extent. Matrix effects are, well, they happen when the presence of other elements in the sample of the matrix influences the light emission of the element you're trying to measure. It can enhance or suppress the signal.
So, like, a lot of iron in a steel sample might affect how brightly the chromium signal appears.
Exactly that kind of thing.
Yeah.
And another issue is self-absorption, where emitted light gets reabsorbed by other atoms of the same element in the plasma before it reaches the detector. This can make high concentrations appear lower than they are.
So how do you deal with those? Just careful calibration.
Careful calibration is the start, but sometimes you need more advanced correction models in the software, or you might choose a different, less affected spectral line for analysis. It requires some expertise to manage properly.
Makes sense. Okay, let's dig into the key components a bit more. You mentioned different ways to excite the sample. Can you elaborate on those excitation sources?
Sure. They really define the type of OES. A very common one, especially for metals, is spark discharge. This uses those rapid high-voltage sparks in argon we talked about. It's great for solid metal analysis.
Fast and effective, you said. Any downsides?
Well, it's mainly sensitive to the sample surface. So if the surface is oxidized or if the material isn't perfectly uniform, if it has inhomogeneities that can affect the result, you need good sample preparation.
Okay. What else? You mentioned ICP.
Right. Inductively coupled plasma, or ICP-OES. Here, the plasma itself is the source. It's an incredibly hot, stable plasma reaching maybe 10,000 degrees Celsius.
Wow, that's hot. How's it generated?
It's sustained by radio frequency, or RF, energy fed through coils surrounding a quartz torch. The sample, which is usually a liquid, gets turned into a fine mist, an aerosol, by nebulizer.
Like a perfume atomizer.
Sort of, yeah. And that aerosol is carried by argon gas into the center of the plasma torch. The intense heat does the atomizing and exciting.
And you mentioned how you view this plasma as important, radial versus axial.
Yes, that's a fascinating design aspect. With radial viewing, you look at the plasma from the side. It's generally more robust, less prone to interference from complex sample matrices, but maybe a bit less sensitive.
Okay.
With axial viewing, you look right down the central channel of the plasma along its length. This gives a longer path for the light, boosting sensitivity so you get lower detection limits, but it can be more susceptible to matrix effects.
So there's a trade-off.
Exactly, which is why many modern ICP-OES systems offer dual view capability. They can switch between or even combine both views, giving you the best of both worlds, robustness and sensitivity depending on the sample with what you need to measure.
Clever.
Yeah.
And the third type you mentioned was glow discharge, GDOES.
You're right, glow discharge OES. So this one's a bit different. It's primarily for solid samples, but instead of a spark, the sample itself becomes the cathode in a low-pressure electrical discharge.
The sample is part of the circuit.
Essentially, yes. Ions from the low-pressure argon plasma bombard the sample surface, sputtering off atoms layer by layer. Those sputtered atoms then get excited in the plasma glow.
And you said this separates atomization and excitation. Why is that a big deal?
It's a really key advantage because the sputtering process, atomization happens first, and then the atoms diffuse into the plasma for excitation. The excitation step is much less influenced by the bulk composition of the sample.
So fewer matrix effects.
Significantly fewer, yes.
Yeah.
This leads to much more linear calibration curves, often over wider concentration ranges. It simplifies analysis, especially for complex alloys where maybe you don't have perfect reference materials.
Any other perks for GDUS?
Yeah, it's also a relatively cool process compared to a Spark or ICP. Less thermal impact, which is great for delicate things like thin films or coatings. And because it sputters layer by layer, it's fantastic for depth profiling, analyzing composition as you go deeper into the material.
Okay, so 3 distinct sources for different needs. Now, what about the optics that handle the light afterwards? You mentioned polychromators.
Yes. Modern systems overwhelmingly use polychromators.
Yeah.
Think of this as the part that contains the diffraction grating and the detectors. Often they use what's called an Echelle grating design, which is very efficient at separating wavelengths.
And the big advantages.
Simultaneous detection. Older systems, monochromators, might have scanned through wavelengths one by one or used multiple slits and detectors for a limited set of elements. Polychromators, especially with modern detectors like CCDs or CIDs, capture a huge range of wavelengths all at the same time,
And that makes it faster.
dramatically faster. It also improves stability because all elements are measured under the exact same plasma conditions. Plus, you use less sample and get a full elemental picture in one shot. It's a huge part of why OES is so powerful for rapid analysis.
Makes sense. You also mentioned purging the optics.
Right. For elements whose strongest emission lines are the deep UV range, like, say, fluorine, chlorine, bromine, maybe even nitrogen or oxygen in some cases, air absorbs that UV light.
So the signal wouldn't reach the detector.
Exactly. So the optical path, the space between the plasma and the detector, needs to be purged with an inert gas like argon or nitrogen, or even held under vacuum to let that UV light through.
Got it. Now let's talk detectors again. You mentioned PMTs are older, and CTDs like CCDs and CIDs are the modern standard. What's special about CIDs? You mentioned non-destructive readout.
Yes. Charge injection devices, CIDs, they have a couple of really neat features. Like CCDs, they're an array of pixels that collect charge generated by light. But unlike standard CCDs, you can read the charge on a single CID pixel without destroying it.
What does that mean practically?
It means you can measure the signal, see how strong it is, and if it's not saturated, you can let it collect more light before reading it again. This gives an enormous dynamic range, the ability to measure very faint signals and very bright signals in the same exposure without the bright ones blooming or overwhelming the detector.
So you can see trace elements right next to major components accurately.
Exactly. CIDs have fantastic anti-blooming properties. And because a readout is non-destructive and you can access pixels individually, you can do things like read just the pixels you're interested in or capture the entire spectral frame.
And that full frame capture, you said it enables retrospective analysis.
Yes. Imagine you analyze a sample today. Years later, a question comes up about a potential contaminant you weren't looking for originally. If you used a CID and saved that full spectral data,
You can go back to the data and look for the spectral lines of that new contaminant without needing the original sample.
precisely, you have a complete spectral snapshot.
Yeah.
You could also potentially identify unexpected elements or use the full-frame data for advanced background correction or matrix stripping techniques. It's incredibly powerful for forensics, long-term QA, or research.
That's really quite something. Okay, we've touched on the family members, Spark, ICP, GD, but let's really nail down their specific roles. Help us differentiate.
Okay, let's start with Spark OES. Think of it as the undisputed workhorse for the metals industry. Quality control, process control. Its superpower is speed and accuracy for solid metals.
How fast are we talking?
You can get a full elemental analysis, including tricky light elements like carbon, sulfur, phosphorus, and steel, in maybe 15-20 seconds per measurement, right there on the production floor.
Indispensable for making sure the metal has the right recipe.
Absolutely. Some newer Spark systems even boast significantly improved detection limits, maybe 30-40% better, for common metal bases like iron, aluminum, and copper.
Okay, now ICP-OES, the trace element hunter.
That's a good way to put it. Its main game is analyzing liquids, or solids that have been dissolved into liquids. Its key advantage over Spark is much, much lower detection limits.
How much lower?
We're often talking parts per billion, ppb, for many elements, and for some maybe even down into the tens of parts per trillion, ppt range. Spark OES is typically more in the parts per million, ppm range, maybe slightly lower for some elements.
So environmental testing, water analysis, things needing high sensitivity.
Yeah.
Exactly. Pharmaceuticals, clinical samples, geochemistry, anywhere you need to find tiny amounts. The main trade-off is Sample preparation for solids dissolving them usually involves acids and can be time-consuming.
Right. And finally, GDOES, the depth profiler.
Yeah. Its unique strength is surface analysis and depth profiling. Because it sputters the sample layer by layer, you can plot the concentration of elements as a function of depth.
So, perfect for analyzing coatings or layers and materials.
Ideal for it. Thin films, galvanized coatings, paint layers, semiconductor materials. It can analyze how thick layers are and what they're made of, down to maybe 100 or 200 micrometers deep. And it does this relatively quickly. Sputtering rates can be quite fast, up to 100 nanometers per second. Plus, it's great for those light elements, H, C, N, O, which are vital in many surface treatments but hard for other techniques.
So, a really versatile family, each with its specialty. Where do we see these making the biggest impact in the real world? Metallurgy seems huge.
Oh, it's absolutely fundamental there. Quality control in steelmaking, aluminum production. They use OES, usually Spark OES, to check the composition of molten metal in the furnace before they cast it.
Catching problems before they happen.
Exactly, preventing costly mistakes or defective products. And then they use it throughout the process, checking billets, slabs, finished products like coils or bars to ensure consistency and meet specifications. It's also vital in manufacturing cars, planes, machinery, verifying that critical parts are made of the right alloy.
What about recycling and safety?
Big roles there, too. In metal recycling, fast analysis is key for sorting different alloys, separating valuable aluminum grades, for instance. OES, especially portable spark or laser-induced breakdown spectroscopy, LIBS, a related technique, is used for that.
And safety. You mentioned PMI.
Positive material identification. This is critical. Imagine a pipe in a chemical plant needs to be a specific corrosion-resistant alloy. If a contractor accidentally installs a standard carbon steel pipe, disaster could happen.
So they use portable OES units to check?
Yes. On-site QA/QC. Verifying incoming materials. Checking welds to make sure the right filler metal was used, confirming components before installation. It prevents mix-ups that could lead to catastrophic failures.
It sounds like it's mostly industrial. Are there more sort of emerging frontiers? You mentioned plasma medicine.
Yeah, that's a really fascinating area. Researchers are using OES to analyze the composition of cold atmospheric plasmas used for therapeutic purposes.
Like for wound healing or sterilization.
Exactly. OES helps them understand and quantify the reactive oxygen and nitrogen species RON-as generated by the plasma, which are thought to be key to the therapeutic effects. And there's even research using OES during electrosurgery.
During surgery? How?
By analyzing the light emitted from the plasma plume generated when the electrosurgical tool cuts or cauterizes tissue, the idea is that the elemental signature might differ between healthy and tumorous tissue, potentially giving the surgeon real-time feedback.
Wow, that could be revolutionary.
It's still research, but very exciting. And of course, OES is a standard tool in R&D labs for developing new materials, new alloys. We even saw mentions of exploring it for analyzing trace elements in hair or fingernails and potential biomarkers for disease.
So a really wide range of applications. Now, let's try and get a balanced view. What are the main pros and cons? Speed seems like a definite pro.
Huge pro.
Yeah.
Especially Spark OES. Results in, 20 seconds or less sometimes. Critical for high volume production.
And accuracy and precision.
Generally very high, especially when well calibrated. Often traceable back to national standards like NIST, which is vital for regulated industries and quality control.
Is it considered non-destructive? You are vaporizing a bit of the sample.
It's generally considered non-destructive for bulk analysis. The amount consumed is tiny, often just a small burn mark left by the spark. For many applications, that's perfectly acceptable. It's not truly non-destructive like, say, XRF, but it usually doesn't compromise the bulk material.
Okay. And versatility.
Definitely versatile. Handles a wide range of elements, lithium to uranium, basically. And crucially, as we said, it nails those light elements on site, which is a big plus over some other portable methods.
And cost and ease of use.
Compared to some other high-end techniques like ICP-MS OES, particularly Spark OES, can be relatively easier to operate on a day-to-day basis and less expensive to run and maintain. And sample prep, especially for solid metals with Spark OES, is often minimal, just surface grinding or milling. That streamlines workflow.
All right, what about the limitations? Where does it fall short?
Well, detection limits are a key one. While ICP-OES is sensitive, it generally doesn't reach the ultra-trace levels of ICP-MS. So for applications needing PPT-level detection, OES might not be sensitive enough.
And those matrix effects and interferences we discussed.
Yes, they remain a challenge. Matrix effects can compromise accuracy if not properly handled through calibration or corrections. And spectral interferences, where emission lines from different elements overlap, can be tricky, sometimes forcing you to use a less sensitive line or requiring sophisticated software to deconvolute the signals. Though GDOES helps a lot with matrix effects.
Sample tape limitations too, right?
For sure.
For sure.
Spark OES needs conductive solids. ICP OES typically needs liquids, meaning solids must be digested, which adds time, cost, and potential contamination risk. GDOES needs flat, solid samples. And portable units can be bulkier than, say, handheld XRF. Also, the open spark in Spark OES isn't intrinsically safe for potentially explosive atmospheres.
And despite being user-friendly, you still need expertise.
Absolutely. Running routine samples might be straightforward, but developing new methods, troubleshooting problems, interpreting complex spectra, and understanding the limitations that still requires a knowledgeable analyst.
Okay, that gives a good picture.
Yeah.
How does OES fit into the bigger analytical picture? Let's compare it directly to a few others. OES versus ICP-MS.
Okay. Both use an inductively coupled plasma, that hot argon plasma, but the detection is totally different. OES looks at the light emitted by elements in the plasma. ICP-MS sends the ions from the plasma into a mass spectrometer, which separates them based on their mass-to-charge ratio.
So light versus mass.
Exactly. And the big difference is sensitivity. ICP-MS is far more sensitive, routinely reaching parts per trillion or even parts per quadrillion. It's the king for ultratrace analysis.
But the downsides?
Generally more expensive, more complex to operate and maintain,
Right.
and often more sensitive to matrix effects, requiring careful sample prep and internal standards. Sample digestion can also be more hazardous.
Okay, how about OES versus XRF X-ray fluorescence?
XRF works on a different principle too.
Yeah.
It bombards the sample with X-rays, causing atoms to fluoresce, emitting their own characteristic X-rays. It's truly non-destructive, very fast, often handheld, and works on solids, liquids, powders with minimal prep.
Sounds great. So why use OES?
XRF's main limitations are detection limits, generally higher than ICP-OES, and its difficulty with light elements. Below, say, magnesium or sodium on the periodic table, XRF really struggles. OES, especially Spark, is much better for carbon, boron, phosphorus, sulfur, and metals. So XRF is great for alloy sorting, screening, analyzing heavier elements, but OES often wins for precise light element analysis for lower detection limits in liquids via ICP.
Got it. And OES versus atomic absorption spectroscopy.
AS measures how much light at a specific wavelength is absorbed by ground-state atoms from the sample, which have been atomized, usually in a flame or graphite furnace.
Absorption instead of emission.
Right. The main practical difference is that A is typically a single-element technique. You need a specific lamp for each element you want to measure, and you measure them one at a time.
So much slower for multiple elements.
Way slower. OES, particularly ICP-OES and modern Spark OES, measures dozens of elements simultaneously. Plus, ICP-OES generally offers better sensitivity and a wider linear range than FlamePay-S. So while ARIES is still a robust technique, OBS has largely replaced it for routine multi-element analysis.
So wrapping up the comparisons, it really comes down to what you need to measure in what type of sample, how quickly, and down to what concentration level.
Precisely. Spark OES for fast metals analysis, including light elements, ICP-OES for sensitive trace analysis in liquids, GDOES for surfaces and depth profiling. They each have their niche, alongside XRF for rapid screening and ICP-MS for ultimate trace sensitivity.
And who are the key players making these instruments?
Oh, there's several major companies known for OES. You have names like Thermo Fisher Scientific, Shimadzu, Spectro, which is part of Amitech, Bruker, Hitachi High-Tech, PerkinElmer, Horiba. It's a competitive field, and they're all constantly innovating.
Pushing the technology forward in detectors, software, automation.
Exactly. Making them faster, more sensitive, easier to use, more robust.
So to kind of bring it all together, optical emission spectrometry in its various forms is clearly a vital analytical tool. Its speed, accuracy, and versatility make it a cornerstone in many industries, and it's evolving to tackle new challenges.
Absolutely. And looking ahead, the future for OES seems pretty bright. We can expect ongoing improvements. Better detectors like advanced CIDs offering even wider dynamic range and lower noise, letting us see fainter signals more clearly.
Pushing those detection limits down further?
Potentially, yes. And also improving robustness. Think about more stable plasma generation, better optical designs, maybe making the instruments tougher for harsh environments or easier to use for complex samples with fewer interferences.
It seems like OES is set to remain critical as industries keep demanding faster, more accurate, more comprehensive analysis.
No doubt. But here's a final thought, maybe a bit provocative. What happens when we really integrate artificial intelligence and machine learning deeply into OES?
How do you mean? Beyond just analyzing the data.
Yeah. Imagine AI not just processing the results, but actively helping to optimize the instrument parameters in real time, automatically identifying and correcting for complex spectral interferences, maybe even suggesting the best analytical method based on a quick pre-scan of the sample.
So it could streamline the whole process, make it even more powerful.
It could. But think about the human element. If AI handles much of the complex data interpretation and method development, how does that shift the role of the analytical chemist? Does it free them up from the meticulous calibration and troubleshooting to focus more on the bigger picture, on interpreting the meaning of the results, on pushing scientific boundaries, making new discoveries? What new frontiers might that open up?
That's definitely something to think about. The partnership between human expertise and intelligent instruments, a fascinating place to leave it.